In this video, we're going to be talking about optimization. And if you're a Calculus 1 student, optimization is really the bane of your existence. It, along with related rates, is definitely a subject that will trip up many students and could determine whether or not they drop the class, to be truthful. It's definitely not a topic I picked up the first time I learned it. I definitely didn't like it that much. And, from an early age in math, when we first start taking math, we always dread word problems. And I think the real reason we dislike related rates and optimization is because they're basically those word problems on steroids. So I'm going to try to make this as straightforward as I possibly can. I don't offer a magical solution to doing all optimization problems. This is kind of just a general strategy that works for me, and I'm going to be going over a few examples as well. So, when you're asked to do an optimization problem, you're always asked to either, like, so a keyword really to look for is you're always asked to either, maximize, or minimize something. You're asked to do one of these things. And that's really what optimization is. We're trying to find something that would maximize profits or area or something that would minimize, like costs. An example would be like, hey, what dimensions would maximize my volume or my area, or um, what certain factors would minimize the cost or maximize my business's profit. That's really the key thing behind optimization is we really want to find what those things are that would determine, what maximizes or minimizes. So, the key thing I always want to do is I always like to just do the first thing I do is I just draw a picture. I draw a general picture that labels it as best I can. So draw a picture. The second step is I just label it. I label it as best I possibly can. And then I look at what I'm being asked to maximize or minimize, and I set up a function. So set up a function based on what you're asked to maximize or minimize. So set up a function based on what we're asked to maximize or minimize. If it's area, then we'd say A equals length times width. If it's volume, V equals length times width times height, and so on and so forth. So we're going to set up a generic function. For is we set up what I like to call a helper function. Set up a helper function. Set up a helper function if needed. Sometimes it's not always needed, and I'm going to do an example of both. If needed. And what we do is we basically get this function, get the function in number 3 in terms of one variable. So get number 3 function in terms of one variable. In terms of just one variable. There we go. And then what we're going to want to do, it's really just straightforward from here. Differentiate number 3 function. I'm just going to say write f of x for function. And find max slash min. And we're done. That's really the main steps behind it. Obviously it depends on the problem, but this is really just a generic template to do. Draw the picture, label it, set up a function based off that picture, set up a helper function. And then number 5, get this function in terms of one variable off using the helper function, using the helper. And then, we differentiate the function and then we, find the max min. Really straightforward. Honestly, I think the big problem behind this, it's not so much, steps 5 and onward. It's really just steps 3 and 4. Those steps 3 and 4 are really what give people the most trouble. And if you can do these successfully, this section should be relatively straightforward for you. I'm not going to waste any more time just talking about this. I could spend a lot of time discussing strategies about optimization, but let's just do an example. Let's just try our hand at an example, and I'm gonna clear this. You can write it down if you want, or take a screenshot, pause the video. I'm just gonna really jump into an example here, and hopefully it'll make more sense. So if you're from the Calculus 1 class I tutor, I'm just gonna be selecting an example from the notes. Um, this is one I think that really helps uh, basically demonstrate how to do an optimization problem successfully. I think that this is a really good example. Okay, so the question says a rectangular field is to be bounded by a fence on three sides, blah, 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 blah. Find the dimensions of the field with the maximum area that can be enclosed using 1,000 feet of fence. So we're looking for a maximum area, and that's how I know this is an optimization problem. We're dealing in terms of maximum things or minimum things. So that's a key word I want to look for. Okay, so what I'm going to do is my first step, I'm going to draw this picture. I'm just going to draw this picture, and I'm a pretty crappy drawer, so cut me some slack. Um, and I'm just gonna. It says that three sides, and then there's a stream on the fourth side. So this looks awful, but it gets the job done, right? So this is supposed to be my stream. Hopefully you can see that. It's not anything else. Um, so okay, so there's the stream, and then all of these black sides are the sides of the fence. So what I want to do is I just want to label this as best I can, and this is a rectangle, so I'm just kind of gonna give it a length and a width. So I'll just label this X and these two sides Y. It doesn't really matter. It won't matter in the end, honestly. So okay, so the first thing I want to do is I want to set up those functions. Over here, I'm gonna call this my maximizing function. My maximizing function. And someone I was tutoring one time uh, said called it the master function, which I find to be a little more catchy, kind of makes this more dramatic. You can call it whatever you want. You can call this like Santa Claus or Easter Bunny function. It doesn't matter, honestly. These are just labels. So this is just the maximizing function. And the maximizing function is the thing I want to maximize. So what are we trying to maximize? Well, we're trying to maximize the area. We're trying to maximize the area. So then we just look back at our geometry knowledge and we, think about that. Well, what's the area of a rectangle? Well, the area, it's just length times width, right? Length times width. Okay, so I'll just say A equals just X times Y. X times Y. Okay, so now you see a problem. Because remember that and later in my steps, I'm asked to differentiate this, but I can't differentiate unless it's in terms of a single variable. So what I want to do now is I want to set up my helper function, my helper function, my helper function. And you usually get your helper function from additional information that's given to you. Like it'll say, maximize the area, and then it's like, hey, here's the perimeter. In this case, it's like, hey, this is the perimeter. We get 100 feet of fencing as our perimeter. And it's like, okay, great. I don't see what I'm supposed to do with that, but okay, that's good to know. And the reason they even throw that in is because that's what's going to help you set up this helper function. That's what's really going to help you get just your maximizing function in terms of one variable. So I'm going to use this additional information and I'm going to make a helper function out of it. So it says all of this is going to be worth 1,000 feet of fencing. So 1,000 and then just the perimeter of this. So we could just say X plus 2Y. Okay. And you see what I did here now. Now all I can do is I can get this in terms of one variable. I'm going to get X by itself because that's a lot easier. So 1,000 minus 2Y is equal to X. You could do it the other way around. You could get Y by itself. You could 1,000, minus X over 2 equals Y. That's fine. It doesn't really matter as long as you just get one variable by itself. So that's really that's the job of the helper function. you use him to basically just get one variable in terms of another. So x is now the same thing as 1000 minus 2y. All I did was I subtracted 2y from both sides. So now, my area function, it's in terms of y, so I'm going to write a of y is equal to what? Well, I'm not going to work with x's anymore because remember, x is 1000, 1000, 1000 minus 2y just times y. And from here, honestly, it becomes extremely easy. We can have 1000y minus 2y squared, and that's my a of y function. So now all I have to do is I just differentiate this guy. I just differentiate here with respect to y. So a prime of y, a prime y, is equal to 1000 minus 4y. Now, all I have to do is I just have to find the max and the min of this. Remember how you do that? You just find the critical numbers. You set your derivative equal to 0, see where it's 0 or undefined. So I'm going to say 0 is equal to 1000 minus 4y. Subtract 1000 from both sides. I get negative 1000 equals negative 4y. Divide both sides by negative 4. And I get y is just equal to 250. Y is equal to 250. And then we have to look at what it's asking us. It's saying, what are the maximum, finding the dimensions that produce the maximum area. Find the dimensions. So it's saying, it's asking for the dimensions. In other words, an x and a y value. So, okay, we have the y value. So how do we find x? Well, all I do is remember what we defined x to be. It was 1000 minus 2y. It was just 1000 minus 2y. So all I'm going to do is I'm just going to take this y and plug it in there to get my x. So my x is equal to 1000 minus 2 times 250. 2 times 250 is 500. 1000 minus 500 is 500. So x is equal to 500. So my dimensions, dimensions, remember you could just say it is 500 by 250. And what are our units? Don't forget to include the units. We're going to feet. So we're going to feet. So 500 by 250 feet. And that's it. So pretty straightforward process. You could see, honestly, like after I got to this step, after I used the helper function, it was really just what we've done before. One thing I should mention is that sometimes you're going to have values, here that will produce, you'll get multiple values. We might get 2 or 3 of them or something. And it's up to you to figure out, hey, which one is which one's going to produce the maximum or minimum value. And and here I only got one result, so I didn't really need to do it. But honestly, like just to show you, I'm just going to show if this is maximizing or minimizing. I'm just using stuff from earlier chapters in Calculus 1, just finding the max and min, local max, local min. So over here, I get negative. Over here, I get positive. And then sorry, no, other way around. Sorry, I get positive, and then here I got negative. And so you can see here, I'm increasing, decreasing. So this is a max. This is a max. And since that 250 is a max, I know that, hey, this is the guy that produces the maximizing area. So that's the one I want. I want where y equals 250. And then I find x based on that, and that's my answer. If you just have one result, it's not necessary to do this. But if you have multiple results, it is necessary. And I'll do an example of that. I'll do an example of that in like just a few seconds. So really straightforward. Honestly, a really straightforward process. Let's go over how I would do this in a different way, and then in the next video, I'm gonna do an entirely different example, and we should be good with optimization. So here, I worked with, I got y by itself, sorry, I got x by itself, but there is a different way to do this, and I'm just gonna kind of run through it really quickly. I don't want to spend too much time on it, but I'm really trying to nail in the point that it doesn't matter which variable you get by itself, as long as you just set up your function right, that's all. Okay, so really quickly. I have A equals length times width. So again, I'm going to write A is equal to x times y. And remember, we're just going to use the helper function. We're going to use the helper function. Uh, so I have 1,000 equals 2y plus x. And I'm just going to kind of run through this really quickly just to really show you what I'm talking about. 1,000 minus 2, 1,000 minus x over 2 is equal to y. Just some really, really quick arithmetic right there. Okay, so I have y by itself. And so now I can define this function in terms of x. So a of x is equal to x times, well, remember what y is. Y is 1,000 minus x over 2. I can basically bring a 1/2 out front, and that'll become a 1,000 x minus x squared. All I'm doing is, this is over 2, and that's the same thing as if I multiplied this by a half. So I just brought out the 1/2, and then I distribute this x in there. That's all I did. Okay, so that's my a of x function. It's my a of x function. Now we just, we just differentiate. So, oops, I haven't taken the derivative yet. Okay, so this is my a of x function. And now I'm just going to write a prime. Well, a prime, just going to leave this constant out front. 1,000 minus 2x. And I can distribute that 1/2 in. I get 500, whoops, not 5,000, 500 minus x. And that's my a prime x, but remember we set it equal to 0 in order to get a max and a min. So 0 equals 500 minus x. Negative 500 equals negative x. Divide both sides by -1 in order to get x by itself, and I get x is equal to 500. And we don't really need to check if that's a max or a min because this is the only value that I get. Now, I take this and I plug it in over there to get y. So I get 1,000 minus 500 over 2 equals y. 1,000 minus 500 is just 500 over 2 equals y. 500 divided by 2 gives me 250. 250 equals y. And that's it. And you can see, this is the exact same result I had. So my dimensions again, my dimensions are just 500 by 250 feet again. So 500 by 250 feet. And that's it. So, I really just reiterated this. I probably didn't need to do it, but I was just really trying to show you that it doesn't matter which variable you pick to get by itself. As long as you just get your maximizing function or minimizing function in terms of one variable, you can see that it's not going to matter. You're going to get the same result anyway. So yeah, it's really with optimization, the tricky part is just setting it up. But after that, it's really a mechanical process, and we're doing things we've been doing basically the entire semester for Calculus 1. So hopefully this was able to help. In the next video, I'll be doing another example, one that's a bit more involved, but also a little bit easier at the same time. So stick around for that.